We have a couple of lectures on data visualization that will be running today and in a couple of weeks. Today's talk is by Patrick Rashleigh, who is from the Center for Digital Scholarship at Brown. And he works on producing and disseminating visual modes of scholarly communication analysis and helps to design user experiences in reaching a variety of audiences. He's a designer, user researcher, programmer, and instructor working in the context of academic libraries. And so we would like to start a kind of discussion at the CTR level about visualization, because it's a very important way of presenting information. And so we're going to start this off by having Patrick kind of give us a very broad overview of what you should be thinking about when you're thinking about visualizing data from your study. So let me turn it over to Patrick, and I will let him tell you how he wants to handle questions, but I will be monitoring the chat as well. So if you've got questions, you can put them there. All right, thanks, Patrick.
Thank you, Chris. Yeah, so the way that this Zoom is set up, I can't see any of you, any of your faces, but I can see the chat. So normally when I do this either in person or with sort of a with the array of faces in Zoom. So, but I'm happy to take comments, questions along the way. There will be times where I'll sort of break and ask if there are any questions, and I'll be asking for a little bit of like audience participation along the way as well. So, so I'll just plunge in, and if anyone wants to say anything, just stick it in the chat, and I'll try and keep an eye on that. So yeah, my name is Patrick Rashleigh. I work at the library in the Center for Digital Scholarship. And this is sort of my 10,000-foot view of data visualization. I realized that before teaching tools, a lot of times it made a lot of sense to have be able to talk about just some of the principles of representing your data visually, as opposed to writing it out in text, which we are all much more better trained in how to communicate via language. But we're less trained in how to communicate visually. And so this was my sort of attempt to fill that gap in our thinking. And roughly this will break down into 3 sections. We'll ask why visualize. We'll take a look at evaluating visualizations and coming up with a simple framework for that. And then also, how do you go about designing visualizations when you're trying to create something? So let's begin here, and we're going to put the chat window through its first set of sort of paces. Why do we visualize? We have language, we have numerical, numbers. You can write out the numbers. Here's an example. You can see all these examples of visualizations, but why do we visualize? And so put your thoughts into the chat. Here's the test to see if there's an audience out there. Ah, yes, Erica. It can be a more efficient way to illustrate findings. Yep. Okay. What do you mean by? Oh, they're all coming in now. So, what do you mean by efficient, Erica, or anyone? How do you follow up that? Yeah. So I'm seeing Haley, quicker, efficient. Let's see. Yes, I think Leslie's onto something. So we have these abilities to see, and I saw someone mention pattern. They have all these facilities in our brains. And of course, this is a medical crowd. This is an easy question for you all. Probably you know more than I do on this, but we have these facilities to be able to see patterns and relationships. Yes, rapid recognition, interpretation, and memory. You guys, your answers are so much faster than when I do this with undergraduates in the humanities. So yes, absolutely. So exactly. There is a different channel going on, and we know this sort of like, you guys know it through your studies and practice, but we know it, I think, as human beings intuitively, that we are able to process things in a different way and at a very sort of efficient high level, particularly in the areas of patterns and relationships. That's the strength. And Something to keep in mind is that the primary purpose of visualization is insight, not pictures. That's coming from Ben Schneiderman, who's the inventor of the tree map visualization, if anyone knows that one. But I think what I like about this quote is that it emphasizes that there can be a temptation to put visualizations in for the sake of visualizations, just to break up the text or give something sort of eye candy type of thing. And that, I think there actually is a role for that, but the primary purpose is it provides a sort of a kind of insight that is not available through other means. So for instance, here's a very, very simple table, 8 values with some categorical context. And, I could ask you to study these, and you may notice certain things, but you'd have to read it over and think about it. One of the things, though, that tables are very, very good at is, if I ask you, what is a job satisfaction for people with a college degree who are 50 and over and who have an income of over 50,000, it's pretty easy for everyone to narrow in on 928, right? So you can just see it, and there's no squishiness there. It's exactly 928. And so tables are really easy for looking up individual values. That's what they're good at. If you want your audience to be able to look up individual values according to criteria with 100% accuracy, a table is your friend. That's a great way of doing it. So we don't want to throw that out. But with graphics, you see something different. So these are the same numbers put into a graphical form. Does anyone notice anything? And I'm talking obvious, nothing subtle. Does anyone notice anything in the data that they didn't notice perhaps in the tabular form? I'm not asking you to overthink it. It should be pretty obvious. Yep, Leslie's got it. 1 line goes down, 3 lines go up, and I think, oh, Milan, you did notice it in the table. Oh, I see. You got have higher satisfaction. Yeah. Yep. Yep. But the fact that 3 are trending up and 1 is trending down, I'm sure we all could have figured that out if we'd studied the table for a while. But in the case of the graphic, you can just see it. It's just, and that's what you're shooting for. You're shooting for that feeling of that sense that we just can see it. It's pre-attentive processing. You don't have to give attention to it. It just pops out. And that's the ideal when you're working with graphical representations, is that's what your ideal state is that pre-attentively being able to process and seeing the conclusion yourself. So, and of course, the power of that pre-attentive processing applies to both communication of numbers and patterns and relationships, and also the analysis. So when you're the primary, as a researcher, you're the primary audience for this, and then you can see those patterns and relationships. And you can see that intermingling of tabular representation and all the power of the lookup, and combined with the graphical representation, and the fact that these two things complement each other so nicely is why you get them intermingling in tools such as Excel, because it's great to have both. Okay, let's poke a little bit at seeing patterns. If graphical representations are powerful at seeing patterns and relationships, let's explore that a little bit more. Here's a bunch of text data. It's on the voting patterns of at least 1 generation of Supreme Court justices ago, and whether they voted with a majority across a number of issues. And you could read over this text and perhaps notice certain things. But let's try taking this and just putting it into graphical form and seeing what happens. So we've taken the last names of the justices, alphabetical order, across the top, the issues that they were addressing, alphabetical order down the side, and it colored this sort of like salmony color. if the justice went with the voted with the majority. So does anyone notice anything in the graphic representation here that perhaps they might not have otherwise? Any patterns jump out? Yep. So Chris, you noticed the Connor, Jacqueline? Yep. So you notice that this pink bar runs right across. There are no issues supported by all justices. Yeah, that's true. Yeah. Yeah. But mostly I'm getting that people mostly saw the O'Connor bar. Yep. So, and that's true. That's under this arrangement, that is the thing that pops out the most. And again, pre-attentive processing, right? You just see it. Oh, there's a bar running right through it. That's a pattern I see. There's another one here that because they're beside each other, it's easy to see that Breyer and Ginsburg match each other. That sort of pops out to my eye. Although I have to say, I taught this a few times before I noticed that myself. But O'Connor's the big one. So, but I'm wondering whether we made a lot of sort of arbitrary decisions in putting together this graphic. We arranged things like alphabetically in both axes. And I wonder whether there are patterns in there that are not being brought to the fore because of some of these arbitrary decisions. So let's just rearrange, do nothing but rearrange the axes and see if anything else comes out. Oh yes, that's there you go. O'Connor is the pattern that pops out here. So now all we've done is rearrange the axes so that they're no longer alphabetical, and you can start to see, a very different pattern, which is that there is a voting block, right? That was not apparent in the last representation. And then you can start to do some interesting things with your eyes. Again, with your eyes, you can just sort of see these blocks, but then you can start doing visual analysis. Like this is one interpretation, although I see that there's a voting block here with everything except Stevens with due process. So then I begin to wonder, well, my eyes wonder, like, what is it about that issue in particular that took Stevens away from this voting block? And you can imagine different shapes of voting blocks. Like, oh, it's, this is a voting block on the bottom right, except for these two issues, Kennedy and Scalia across due process. So it's interesting. Due process seems like an interesting area to investigate. So these are all things that you're doing, that kind of analysis you're doing with your eyes, right? Yes, Chris, yes. You're doing it with your eyes, which is exactly what you want with a visualization. You want to be doing all that work in your sort of like, your visual cortex. But notice the point of that exercise was to show that that little decision about how we arrange the axes was a decision that had a pretty profound impact on what was on the efficacy of that visualization. And there are 1,000 little decisions behind visualizations that you're going to make that will make them more or less effective. So, for instance, a big one is what kind of chart are we going to use? This is the data we were looking at before in two different chart representations. The data looks different in these two representations. So just like with the arrangement of the axes, different things come to the fore. And I'm not going to say that one of these is better than the other, but I will say that certain things come to the fore, certain patterns and relationships come to the fore depending on which chart you're choosing to use. So, for instance, can anyone tell me what kind of pattern or relationship is easy to see on the left-hand visualization? Or put another way, what kind of question does this visualization answer because of the way it's designed? Yeah, it's grouped by age. So that means, it's easy to sort of like, it really, the way that this has been designed, it allows you to answer the question, what is the job satisfaction as distributed across within an age group? Yeah. Yeah. So I think it's a bit awkward to have I'm not a big fan of these of legends, but you can see that the shape relative to the college degree and income level, you can see the shape within the age group. So it's very easy to make the comparison within the age group because of adjacency, right? It's easy to see how the orange pokes up in the 50 and older category because it's immediately adjacent to the blue bar and the green bar. You know, it's easy to visually make that comparison, right? It's much harder. Yes, yes, Mary. I'm responding to, I believe, I don't have your view, so I can't tell, but I gather you guys can either choose to send it to, I think I'm called a panelist and attendees. And if you don't send it to the panelist or the host, then I can't see it. So but if you want to compare between the age groups, say the folks with college degree over 50,000 and see what's happening between the age groups, that's a harder question to answer visually in this left-hand representation. You have to draw kind of an imaginary line between the top of the orange bar here and the top of the orange bar here and do sort of a comparison. And what you're doing in your imagination is you're bringing those two bars together and comparing their heights. And so whenever I think that the audience has to do something like that, some manipulation in their imagination, I consider that work, right? And that work means that it takes away from the pre-attentive processing. It makes it harder. Whereas if you go over to the right-hand one, you can see what they've done is they've taken those two heights and they've put it and actually done the work of connecting the lines. So you can actually see what's happening between the two. So they've removed that work. So this is a much better representation of the change between those two categories simply because of the way that they've chosen to design it. So there are different strengths to each of these visualizations, depending on what you want to communicate. Yes, Chris, there's that often comes up, that people are uncomfortable with there being a line. And I'm not sure, it's an interesting question. I think it's a convention, right? And we'll return to conventions when we do pie charts, but whether people still read that convention, particularly when they have two clearly labeled categories at the bottom as a sort of a linear interpolation, I don't know. I'm not sure, but it may be the case. So you do have to be careful with lines that you're not implying sort of like that it's a smooth transition between two values. So yes, yeah. But you have something like this. I'm not going to linger on this too long, except to say that you have something like a scatter plot matrix, which is basically, for those of you who don't know this, it's just a scatter plot. But what they do is you take higher dimensional data. I think there are like a dozen dimensions here. And when you want to compare every dimension to every other dimension, you can put it on a matrix so that, for instance, what's the relationship between restaurants and food and say housing quality? Well, you take restaurants and food is the y-axis here, and housing quality is the x-axis down here, and they meet right there, and you can compare the two. So it's a really powerful way of combining, of looking at every dimension with every other dimension and looking for correlations. And it's a way of doing it that uses your eyes. So apart from the startup time that it takes to explain what a scatter plot matrix is, now I have like this, like 10-dimensional data, and I can cast my eye across this matrix and immediately just start picking out areas of high correlation. I can see high correlation, high correlation, high correlation, low correlation, low correlation. And this is incredibly, when you think about the kind of statistical analysis that you're doing with your eyes, with this 10-dimensional or so data, it's remarkable what a well put together visualization can do just simply using visual means. So again, I use this as an example of where I think a visualization is really powerful, and the potential for using this part of your perception. So that sort of closes out the why visualization opening section. Any comments or questions before we move on to evaluation? I'll just give you a few minutes, a few seconds. Okay, I'm not seeing any. So I'll just move into the next section. So again, choices. How do you put together and choose your visualization? These are two very different visualizations of the same data. I think we're kind of familiar with the word cloud format. I remember when it first came out, they were called Wordles, and they were all the rage for a while. It represents word frequency, right? Generally speaking, it's how many times does this word occur within a certain number of other words. So we can see that no and said are the most common words in this passage of text. And down here, you can see said and no, oh, and shall as well. So you can see it's two ways of representing the same data. So which is better? In evaluating it for people who are not specialists, I came across this. I didn't come across this. Is a very famous piece of research based on a very famous piece of research, sort of seminal research that was done in data visualization in the mid 80s by Cleveland and McGill. It's a very short paper. It's very readable. It's only 10 pages or so. But basically what they did was they tested the major means by which you take a number and represent it on the page or on the screen. And it turns out there aren't that many ways of encoding a number visually. And what they did was they just tested across a population how efficiently and accurately people could translate back and forth between numbers and their visual counterpart. I think I'm slightly misrepresenting the study, but that's basically what they were doing. And they found there's a hierarchy that certain ways of encoding numbers are better supported by our perceptual system than others, or if not better, at least more accurately and quickly. So the most powerful by quite a bit was when you encode a number with length. So if you code a number with length, we can decode that very, very quickly. So I don't think I'll do it now in the interest of time. Let me check. Yeah, I'm gonna keep it going, but well, actually, let's do it quickly because it is kind of fun. We have these 3 bars up here, and if everyone could just, without thinking about it too much, if I tell you that this first bar on the left is 10, can people punch in the chat what the value of the second bar is? And we'll just get a quick sense. 6, 7, 8, 7, 7, 7, 7, 7, 7, 7. Good, great. 7, yep. Yeah, right? I mean, we're all zeroing in on that pretty darn quick. There's a little bit of variation. We had 1, 6, maybe 1, 7, 1, 8. But basically, we're all in that 6, 7, 8 thing, and we're really gravitating around 7. And I think those came in really, quickly. So I think I doubt many of you, yeah, you'll want to. It came in very quickly, and I think it was not hard for you guys to do that. I think I'll get back to that, Mary. I hope I'll answer that. I think that'll come up again in a second. So accurate and quick, and I don't know what the accuracy are. I haven't actually taken out a ruler to check if it's actually 7, but the fact that we all sort of agreed upon it quickly is I think the important thing. And if you shift the baselines a bit, as we see down here, then it becomes a little bit harder. If I were to ask the same question across shifting baselines, maybe you guys would hesitate, maybe there'd be a bit more variation. Length is kind of the same thing, again, shifting baselines, but overall, it's still a really powerful, easy way for people to perceive numbers. There's actually a pretty big gap, I think. It doesn't look like much on the screen, the way it's laid out, but there's a pretty big gap between these ones and these ones over here, where angle and slope, they are both, you can translate between the two, but it becomes a lot, it's harder. And I won't do that exercise again for these guys, but if I asked you if the angle is like 15 and I ask you what that angle is, we'd probably get a little bit more variation, and people would have to think a little bit harder. And even better, if that V shape were like tilted downward like this, keeping the same angle, then I think people would have to really think a lot harder. You'd have to be in your head rotating it back to the right angle and trying to compare the two, and then sort of saying, well, it's probably around this. There's more work involved, right? Same with the slope. I think slope is helped by the fact that we're all used to reading analog clocks. I think that helps us in judging angle. But you have area and volume. These are actually, although they're quite common, particularly area in data visualization, data visualizations to encode numbers using area. It's actually a really hard means to decode the numbers behind it. And I am going to do this very quickly. I'm going to say, like, okay, if this big one here, I'm going to say this big one here is 50. Can people punch in, without peeking at other people's responses, what this one here is? If this one's 50, what's this one? So you guys, a lot of you are dividing by 10. Suzanne has a 16th. Yeah, so most of you are dividing by 10, and we got a 10, like we have a 10 as well as a 5. So there's more variation. You guys centered in on 5 a lot more than most people. Most crowds, it's all over the map, and people are kind of thinking about it for a while, and there's a sort of more uncertainty. So, but in general, you can see that there is a lot more variability, right, within that. I mean, we're going from everywhere from sort of 1/16 to 10, so 1/5. So and that's because it's hard. We can't just perceive it. We have to engage in some sort of strategy, I think, in terms of packing. Maybe I sort of think about in terms of packing the smaller circles inside the big circle. And this is even worse. My strategy is even worse for volume, because then you have to like take the 3D images of the boxes, like the 2D images of boxes, convert it into 3D in my head, and then pack the little box inside the big box to try and make those comparisons. It's a lot of work in terms of cognitive work on the part of the audience. The 2 ears. Yeah, I don't know. I haven't actually gone in and checked any of this in terms of like how big things are, or I'm not sure. They look close, but not quite the same to my eye. Yeah. So and then you get down to things like color intensity, and color is great for I mean, in terms of the color hue, there's really no quantitative implication to color. I mean, if I ask you what if I say the yellow is 10 and I ask you what the purple is, well, it's a nonsense question, right? So it's really only good for generic or categorical comparisons, to say like the yellow is not the same as the blue. It's very good for that, but it's not good for representing numbers. And color intensity is also very difficult. You can do numbers with color intensity, but it's much harder to like pick out an accurate sort of numerical translation. You can see generally that, oh yeah, this is more gray and this is more blue, but it's hard to say like, oh yeah, if this is 10, then this is 5 or whatever. Was it Mary who was asking about like, why would you want generic comparison? Well, we'll come at an example in just a moment. For instance, so moving back, how are these numbers encoded in the word cloud. There, we know the numbers are word frequencies, but what visual means is the encoding, are these numbers being encoded from our last, casting your mind back to the last slide. What makes a number larger in this visualization? How can you tell something, a number, the frequency is higher? Yeah, bigger size, exactly. Yep, size. I have no idea. Yeah, volume. If it were a 3D word cloud, it would be volume. Yep. So area, right? And remember how weak area is relative. So area, and that's so it's relatively weak. You can tell something is bigger than the other, but it's not so easy to translate back to, hard numbers or even just proportional numbers. And then how is it encoded in this example here on the left, the bar chart? Length. Thank you, Roman. Yes, Rockwell. Length, right? Which is a very powerful way of encoding. So I think the data visualization people, I can tell you right now, because I've been in conferences where the data viz person basically says, I hate word clouds, because they say it's a very weak encoding method. And somebody asked about the colors. The colors are meaningless, right? They're just purely aesthetic. But I disagree. I don't think word clouds are always bad. It is true that you can read the numbers and compare the numbers much more accurately in a bar chart such as this. But on the other hand, the word cloud reaches audiences in a different way. If they're aesthetic, they grab people's attention. And I remember, particularly when they were novel, I can remember a word cloud being introduced, some 10, 12 years ago in an English lit class. And when this was, when it was still called Wordle and it was a brand new thing, people were so excited about it, and it precipitated so many conversations that I'm sure would not have been precipitated had a bar chart been presented. So it really depends on what you want to communicate, how important it is that the accuracy be there versus just sort of a general sense that know and said and shall and time are generally more common than saw and old and face. It really depends on what you want your audience to get out of it. Yeah, exactly, Terry. Exactly. Sometimes it's just about sparking an interest or wanting to dig in. But it really depends. Other times a word cloud would be grossly inappropriate. So, and likewise, here's an example. This is an example that somebody found. It's the Arctic death spiral. It's talking about what we all know, which is the polar ice caps are shrinking. It's laid out in this sort of round format, this radial format that suggests many things, including the lines of longitude converging at the pole. There's a lot of metaphor with that, as well as like the spiral shape that refers to the Arctic death spiral. So there's a lot of sort of metaphorical, and people like circles, people like the colors. I gather this is a very popular visualization. In terms of communicating the numbers, this is a much better way of doing it. That basically you can see much more of the details of what's actually going on. This little line of the squiggly area here, it's kind of hard to see what's going on with the radial format, but it's really easy to see here because when it's laid out in a more linear way, where you're in this one, you're measuring height and length, but it's compromised by the fact that you have this shifting rotational reference point. So it's really hard to compare lengths when the lengths are in different directions, right? So this just like straightens it all out and makes it much easier to perceive. But here, there's so much of the people really find this really appealing and interesting, and it grabs people's attention, and it works at these metaphorical layers. So I still don't think this is a good visualization, but I can see the argument. Here's one that has no excuse. This is a bar chart, and I came across this in something that got sent into my inbox, and I just thought, this is so bad, I'm going to include it as a teaching moment. It's basically a bar chart, and as we know, length is a very powerful way of encoding numbers. But look what they've done. They've shifted the baselines, and then to make it worse, they curl it up and over so that it's really, really hard to compare the length of this to these two. It's so hard that in fact they decided to put the numbers in just so you wouldn't have to do the work, and in which case, what's the point of having the visualization? So I think this is an instance where, again, knowledge of how you don't want to compromise that pre-attentive processing power by doing goofiness like this. But again, it's all a matter of audience. This is a fairly straightforward chart, easy to read. A data visualization person would say this is a good visualization, clean. But this actually was used by an artist to do this. And it's the same data. If you compare the line of the horizon of trees, it's the same as the line we saw before, but it's part of a watercolor. Is the data easier to read here? Definitely not. You get the rough idea that, it's going up, but the way she framed it in a sort of an aesthetic way meant that it has it communicates a very different information, right? Not worse or better, just very, very different. And of course, you have to have the certain context for this to be effective. It makes a lot of sense. Same artist, different data, same artist. It makes a lot of sense in this context, right? If you took that very more straightforward line chart and put it on the cover of Time, it probably would not be nearly as effective as an arresting visual like this that gives you some sense of the data, but also layers on this sort of like emotive quality, eye-catching, engaging. So context matters. I'm just going to check my time to see. It's 12:41. We're going to quickly take a look at the pie chart. People love pie charts. Data viz people find them highly problematic. So we're going to do a quick critical evaluation of pie charts from the perspective, again, of visual perception. So the pie chart, as we all know, is a very popular way of representing a part-to-whole relationship, right? We talked about conventions popped up earlier with the lines representing continuous change. The convention behind a pie chart is that it's a part-to-whole relationship, right? This is something that's actually not inherent to the pie chart. It's just an understanding. It's an agreement between the audience that those pieces add up to a whole, and that the whole is 100%. Sometimes you can forget. Sometimes you can forget in a very public way that in fact everything should add up to 100%. But examples like this are hard to come by, where people have forget the convention behind a pie chart. You can see the date. For those of you who, this is ancient history, but it's a fun one to pull up. But the thing about pie charts is how are numbers encoded in pie charts? Like, what makes you know that a pie is, area. So the area of each wedge, proportional. I would say proportional area, right? It's all fake. What goes along with area? Area and something else go hand in hand. Angle. Thank you, Rockwell. Yes. So area and angle. Oops. Oh, Java. Sorry. So area and angle make up the pie chart. So if we look at area and angle are quite far, again, over to that right-hand side of the slide. And you may think like, well, so what? Big deal. They're still effective at communicating numbers, but let's take a look at that and see what the implications are. Okay, another audience participation. Could you guys please put into the chat just the order of colors that you see? So just name the top three, let's say. The biggest wedge, the second biggest wedge, and the third biggest wedge. And just list them in the chat when I make it appear. Okay, and don't think about it. Just do it like, what do your eyes see? Go. Yeah. There's a fair amount of variation going on here, right? Right? I don't hear a lot of agreement. And there's always one person, you're it, Chris, who says like, this is a trick question. They're all the same. Okay, so remember, these are numbers encoded with area and angle. Let's re-encode them using length, which we know is a much more powerful method. And I think in the interest of time, I will just let you come to your own conclusions. Same colors, same numbers, right? It's not a hard question now, right? And it's really easy to see. It's really, you can just tell what's going on with your eyes. You don't have to, think about it or puzzle over it. And in fact, the numbers are not that close together. If you put a line, it was, difference between what, 23 and I think it's 17 or 18. That's a pretty significant difference between numbers. So they are not all the same. So that's the difference. That's the power of encoding in one method versus the other method. And you can see these are the two, this is much further along to the left. Here's the bar chart, here's the pie chart. And this is just for fun. I won't linger on it too long, but I came across this as somebody had said, well, what if you just encode a pie chart just using area and take out the angle? And that's what it looks like. Here's area plus angle, and this is the angle is all the same and just the area. So if you ever wondered, what if you took out that redundant encoding? That's what it would look like, which I thought was kind of interesting. That was a sidebar. This is a second sidebar note. Just note that all the problems that with area and angle encoding are made worse by introducing 3D into the deal. Again, what are you asking your audience to do, right, with their imaginations? With a pie chart, what you're doing is you're saying like, okay, here's a wedge here and here's a wedge here, and you're asking them to compare. And what you have to do is you have to rotate them in your head together and sort of like try and line them up and figure out which one is bigger and smaller. It's a ton of work for you're asking the audience to do, and then to tip it into third dimension so that now in their imagination, they also have to tip it back up, because this distorts, right? If you're in 3D, this distorts the one that's like closest to you, it becomes unnaturally large. And so you have to like account for that distortion as well. So this introduces so many problems, 3 dimensions. They look cool, but it makes a really simple number series like this really hard to decode. Again, I'm having to in my imagination, cast the tip of this, this cone thing to the back wall and then run it over to the number line over here. It's a nightmare of imaginary lines running everywhere to try and decode these numbers. And actually I just punched in the numbers 40, 30, 20, 10 and asked Excel to give me this visualization, and this is what it spat out at me. So I didn't even like have to make this up. And then 3D also can hide data behind other, like when you layer like that, you can end up like, you can see that the yellow line here passes behind the green block, and you can't see it. It's just don't use 3D. It's just a bad idea. So that was my little 3D sidebar rant. And so, if you're supposing you accept that, okay, pie charts are not the greatest, at least for some things, when you're really worried about the accuracy of numbers, what are the alternatives? Well, here are some alternatives. None of them are perfect, but here are some alternatives to get you thinking. If you really are set on circles, you can keep the pie and then represent the wedges like this. This is a lot easier to compare between the wedges. You keep the part to whole relationship, like you can see that the wedge is part of a whole, but they now share a common baseline, right? And so it's a lot easier to see how the wedges compare with each other. So that's one possibility. This is a sort of a flawed possibility, but it's something to keep in mind, is that you take the idea of length, and then you can combine them as a part to whole relationship, but along a bar. And this can be effective if, for certain data sets, if you are showing change over time, you can stack those bars along, and you can see maybe that the green wedge gets bigger, smaller, things like that. So that's one possibility. It retains the part to whole relationship. But they're hard to compare, right? The thing about these guys is that they're hard to compare with each other. They're easier when you're comparing the greens down a line of them, but they're hard to compare what this turquoise with this green. So if you just take them out and put them side by side, well, you're left with, our friend, the pie chart, the bar chart, which we know is a very effective way of communicating. Cliched and boring as it is, it's very good at what it does. But here you've lost that part to whole relationship, right? You no longer have, apart from the percentage sign, you no longer have that sense that these are values that are part of a larger whole. So, you might think about something like this, and this is a popular way of using the power of length as an encoding method, but keeping that part to whole sort of implication to the data. And here's an example of basically something that could have been handled with a pie chart, but I think is more effectively handled with some combination of different kinds of length-based encodings. And fortunately, we have to zip through this because we're short on time. But I think this works better for what they wanted the audience to do. And as for change, all the problems with pie charts changing over time get compounded when you try and show change over time and compare wedges between two different pies. Much better to do something like this. This is different data, but you get the idea. You can show change better like this, or through some sort of a slope chart like this. This one does not have any part to whole implications, but it probably shows change better. Okay, we're blasting now. Last 10 minutes, design. How do you go about designing a visualization? This is my sort of rule of thumb. I don't have too many rules apart from stay away from 3D. Be intentional in your choices. As we saw, little choices can have big impact on the efficacy of a visualization, but be intentional and start with the idea of, like, what do you want your audience to see? Like, what do you want them to be able to see without thinking, just seeing it with their eyes when they look at your visualization? That's a really important sort of like first step. And then once you've decided what you want them to see, make sure that it is easy for them to see it. They don't have to work to be able to see what you're trying to communicate. Very simple communication principle, but it'll take you a long way. So really define what you're trying to show, and keep in mind this hierarchy of encoding methods. So Mary asked, like, when would you use like colors? Well, colors are, or when would you use categorical, more general comparisons? They're fine if you just want to place things into buckets or broad categories of low versus high or big versus small or something like that. They're absolutely fine. But as long as that's not important, that people be able to see very fine gradations in your data, right? As long as it's fine that they just have a general sense of proportion, then by all means, use all these encoding methods down here. If it's important that people be able to really get the detail of these numbers, then use these encoding methods. And also just be really super clear about what you're trying to communicate, right? So this is a visualization, actually what they call a physical visualization. Here's a kid growing up. And anyone who's had kids or been around people who have kids who are proud parents will know that there's the inevitable conversation of how much their kid grew last year. It's like, oh, yes, so-and-so grew so much. I can't believe how big they're getting. Every parent falls into that trap. So what if we want to visualize that data? Here's the source of the data. Well, you can visualize it like this, right? You can say like, how tall is Bob? And you can just like plot it as a line. But here, I think what we're doing here is we are misreading the requirements of the audience in this conversation. Generally speaking, when folks get together and talk about the size of their kids, they don't say like, generally it's not about their absolute height, it's how much they've grown in the last year. I can't believe he grew 5 inches last year. It's really what we're talking about is this, right? It's the difference between the blue bars. So rather than having your audience have to sort of like figure out what the change was, if the subject of what you're talking about and you're trying to communicate is the change, then don't make your audience have to figure it out by drawing some sort of an imaginary line over and that kind of thing. Call it, bring it out, make it, maybe pull out, you leave it like this, where you have both side by side, or maybe you extract, say the blue is irrelevant. How tall they are now is irrelevant. It's just about how much they grew last year. And maybe line them up like this so they're even easier to compare. Now you can see like, oh, actually they didn't grow as much last year. The year before they grew like, looks to be about twice as much. So all these visualizations are fine. They could all serve a role, although I think I have my doubts about this one here, but they all answer slightly different questions. It's kind of like the exercise we did at the beginning with the bar and the line charts. And this will help us evaluate and design things like this. So this is obviously a map with some sort of data. I don't know what it is, but you can see that it's encoding position, right? So position is basically like length. You can see that the bubble is placed. This one's placed over Poland. And you can see it's encoded with a color, and you can see it's encoded with size, right? Those are the 3 means. So this could be a terrible visualization if it's important that people be able to decode the colors, because I can't decode the colors. I can tell that these are blue, roughly the same kind of blue. I see that this is a darker blue, and I can see this is pink, and this is a darker pink. But apart from that, if you ask me to translate those into numbers, I'd be lost. But if the idea is simply to start to group things and say, yeah, the dark blues are kind of like the light blues, but they're just a little bit different, then this could be a great way. And this is an example where that sort of like general encoding works perfectly well, because you're communicating what you need to communicate. Same with size. It's really important we know exactly like that this is 10 and that this is 3, and it's important for your audience to know that, then maybe this isn't so good because it's hard to tell. It's hard to decode those numbers. But if it's just to roughly say, look, whatever's happening in Germany is approximately 5 or 6 times as much as whatever's happening in Denmark, then that's fine. So it really depends on what you're trying to communicate. Good graphical artists do account for color blindness, and certainly within visualization, actually more in the data in the web publishing world, we're always mindful of trying to look out for those colors that can't be decoded by a significant portion of the population. So yes, Chris, we should always keep that in mind. So in long story short, choose a chart type that fits your purposes. And there are lots of resources to do this. I can share this. I'm going to have to zip through because we're running out of time. If anybody wants to, I'm happy to send a copy of this presentation to whoever wants it, and you can grab those URLs. Normally, I have a handout when I'm doing this in person. So, but these are places where you can find visualizations that match your requirements. And I think Chris is getting the hook out. So I will.
No, I'm just here. I'm just here for when I'm needed. So.
Oh, okay. But we have
going.
2 minutes left. I'm going to do, I'm just going to blast through this, which I think is an important point, which is that a lot of our rhetorical arguments take place over several visualizations. So if you're going to do that, if you have like 3 maps or 3 visualizations that you're meant to see together in order to see a larger trend or a larger narrative, then make sure again that these are chosen and placed with respect to each other in a way that allows for those patterns to emerge. So for instance, here's an example of we're trying to track something. I'm trying to track the star, right? And we say, oh yeah, well the star goes here and then it's down here and then it's down here. Well, it's really hard to see what's going on here because of the way the change of color, the change of size, the way that the background is shifting behind the star. This is not an easy thing to see the trend of the star. Whereas if you engage in what's called small multiples, somebody mentioned Tufte. So whoever knows Tufte will recognize that term. They're all the same size. They're placed side by side in a sequence. The background is not shifting. The only thing that's changing is the red square. So it's really easy to see what's going on between here. So this is set up in a way that invites that comparison. Again, making it easy for your audience to see this. Take out more details. It's even easier. When you do it right, like the New York Times did, it means that you can make these comparisons of really interesting data just by casting your eye across and almost watching it like a movie. And this only happens when you really essentialize and brings to the fore the changes as opposed to putting in lots of extraneous data. You can also do it like this. This is another way of representing change. That way you compact the multiple visualizations into a single. Or in the, we're presenting now more and more on screen, so you can do things like that to show change. So again, just make sure that whatever it is you want to show between these multiple visualizations are easy to see for your audience. And so the final summary I leave you with, in general, these are basic communication principles, but just ask yourself as you're authoring a visualization, make sure that the problem or question that you are addressing is very, very clearly defined in your head. Like, what is this visualization? What problem is this addressing? What is your data saying? What is the data actually communicating about this problem? And make sure you're clear about your audience and your context. Presenting on a slide is different from presenting on a poster, which is different from printing in a journal. Your audience may be an expert audience and maybe a lay audience. All of these have impact on the way you choose to represent. So if you have all three things working, you look at your visualization. Does it work with all the three of those things at the top? And if they do, then you're probably in good shape. If even one of them fails, you may want to go back to the drawing board. Okay, and that's it. So I can hang around. It's 1 o'clock, so you're all, the time is up, but I'm happy to take questions or have a discussion or whatever you like.
So thanks a lot, Patrick. I guess we'll see if anyone has any questions, although a lot of people probably have to get off. I just wanted to mention that we are going to have another visualization seminar. I think it's on May 13th. The notice will be going out, and it's going to be on GIS mapping. So which is a very common topic these days. And hopefully we'll be getting some feedback on how people like this and whether we want to follow it up, because I think a lot of people might be real interested in how to design some of these things, and we might even think about workshops that could do that. And Patrick, I may draft you for my intro stat course. I'm teaching to the undergrads in the fall, so I may draft you to come in and talk about this, because my experience is that, particularly with public information, newspapers and websites, it's very easy to mislead people. And I did notice that visualization you had that was so bad was from Fox News, which was not surprising to me. But anyhow, there are a lot of bad graphics out there. So so yeah, Amanda's put the registration in the chat for the next talk. This will be recorded and you can find it on the website. And I know, Patrick, you said you'd share the slides with people, so we'll work that out as well.
Yep.
There is one question in the chat.
Yeah. I'm seeing, is it Romans?
Yes.
Yes. Yeah, it's funny. I was just looking at network visualization is really an interesting challenge, and I'm actually doing a little bit of background research on this. Thanks, Kevin. to try and see. Roman's asking about co-occurrences and network maps, and the kind that usually is represented by a bunch of like bubbles or dots with lines between them. And the bubbles and dots, the bubbles and lines approach has certain advantages, but they're often really, really hard to read and get any useful information out of them. I'm not a huge fan. Sometimes they work if you want to show broad clustering and just show, you know, like broadly the categories of interconnectedness, or if there are very few nodes, then you can make sense of it. But a lot of the time it's just like, it just looks like a hairball.
Well, one thing I do a lot of stuff with network meta-analysis, and so we're often drawing networks there. And you can actually, there are programs that will allow you to rotate the vertices and the edges in such a way that it makes it more readable. So for example, if you have two groups that talk to each other, but they don't within, but not between, that could be very misleading on just a big sort of circle graph. But if you can actually set it up, you can see the separations quite well.
Yeah.
But a lot of people don't know about that. So I was also kind of wondering, because one of your slide, the Wordle slide, for example, that was great for depicting marginal distributions of words, but like which words co-occur would not be something that, but you might be able to encode that somehow, I don't know, by color or location or something, but I don't know if people have done that with word clouds.
Not word clouds, at least not that I'm aware of. I think co-occurrence, usually they visualize as, there's something called like it's sort of like I've forgotten what it's technically called, but it's basically a tree visualization. And you can have the word that you're interested in, and then there's a tree, there are branches coming out for every word that follows it. So if they're, you know, if the word occurs 10 times, then it'll have an itemized list of every word that follows it. And then, you know, and then they can be sized according to how many times that word follows it. And then and then there can be branches out from each of those, and the branches can go both ways. So that's I've seen very effective visualizations.
And that's probably very useful also for natural language processing when you're trying to come up with n-grams and things like that. You know, sets of words that go together.
But yes, the matrix, I'm a fan of the co-occurrence matrices, Roman. I like them. I don't think they're perfect, but they do reveal something different. The trick with those is that it's very hard to follow a path. Like you can see when something co-occurs with something else. So it's like how often do these two nodes get connected? That shows up really nicely in a matrix, but it's hard to sort of look at chains of nodes and paths within the graph network. So I'm still sort of doing some research myself about different alternatives. I've also seen like networks arranged on a circle. I forget what they're called. Maybe arc. I can't remember. But you put the nodes around a circle, and then you have arcs between the different nodes. But it's arranged in a sort of a circular space rather than just sort of across the two-dimensional field. And that can be useful as well. That you'll see different things than if it's sort of like a force-directed graph.
Right. Although if you start connecting those nodes with lines, they start crossing, and at least I know one of the rules of thumb is you want to have as few lines crossed as possible. I mean, there are some wonderful principles for graphics, and you know, I think it would be really helpful to, you know, to put together a workshop, or maybe you know, a set of workshops to talk about that with people who are developing graphics, because you know, I'm actually working on, I was actually going to send you a paper. We've come up with a new plot that we're calling an origami plot, which is sort of a generalization of a radar chart. But I'm also, like in all the students I work with and all the projects I work with, this is like the key thing, is how do you visualize the information so that it's most informative? And it's a really hard thing to learn, but I think it's crucial. So the more you start thinking about that early on and get away from all the tables, the better. Well, it seems like we've run out of questions. So thanks to everyone for coming, and we'll look forward to seeing you in a couple weeks. And have a good weekend.
All right.
Okay, bye.